what are some uses for Azure Spatial Anchors? There are multiple apps that you can create with Azure Spatial Anchors. A really good use case is anytime that you need to tie a specific information to a specific place. For example, if you're in a big building and if you want your users to find their way around, you can put breadcrumbs around and they can detect these spatial anchors and find their way. Another good use case is if you're in a big supermarket or a warehouse and it's really hard to know where things are, you can put specific product information to specific places. So when you're far away, you can see which way to go depending on your purpose. And these are all business use cases. For a more fun application, check out Minecraft Earth.
Hello everyone, I'm happy to welcome Andreas Erben, who will talk to us about developing with Kinect for Azure and understanding the human body. And without further ado, I'll hand it over to Andreas and take it away.
Okay, just making sure, is my screen sharing well? Thumbs up, thumbs down? I guess it is. So
yes, it's fine.
Okay, so my name was already mentioned. I put my title today as CTO Metaverse. In general, I'd like to play with technology and call me a megalomaniac if you want. So we'll talk about Kinect for Azure, or I think it's meanwhile called Azure Connect, and a little bit of understanding of the human body. About me, I'm actually in the United States usually, but currently visiting Germany. So my infrastructure is a little bit limited. I'm at my old parents' house, so bear with me if any hiccups occur. I have over 25 years of experience, worked with virtual reality already in the mid-1990s a little bit, but there was no money in that and no future at that time. So I went into more enterprise type of consulting and connected all types of systems with integration middleware. But I went back to fun stuff probably around 6 years ago when Kinect for Windows became more popular. Actually, it has been 7.5 years now. And started also dealing with HoloLens and use applied AI. In general, I try to tell interesting stories with technologies. So we'll jump right into Kinect sensor. What is this whole thing about, right? So first of all, where's this whole thing coming from? So Kinect initially was a gaming device for Xbox 360 and was released in 2010, so 11 years ago. It was a so-called structured light sensor. And you know what happened? People were like, hey, this is really cool. I want to use this as an app developer. And they somehow hacked the API and released like an unofficial API. So Microsoft was in a little bit of a bind and thought, what can we do now? Do we stop all this? And they which was unusual for Microsoft at that time, they embraced the hacking community in a way that they said, we're going to release actually a product that's meant for people to hack against and to also develop professional software and release an API. So they made available what's called a skeletal tracking or body tracking as part of an SDK. And at that time, it had 20 joints and landmarks. It was just basically a USB device you connect to your computer and a little power adapter and the Kinect camera. 2013, Kinect One came as part of Xbox One. And similarly, shortly after that, Kinect for Windows version 2 was released, which has improved body tracking, more joints, landmarks, and a fundamental new technology in terms of how the camera that senses depth information works. In 2018, we were in a little bit of a tough spot as Kinect fans because earlier, either 2018 or 2017, Kinect for Windows version 2 and Kinect for Xbox was pretty much discontinued. The story is long, why it happened, but it just didn't have enough pickup in the community, in the ecosystem. And so there was a little bit of teary eyes for a few months, but then Project for Kinect for Azure was announced, and it belongs to Azure, the Azure ecosystem. Why that makes sense, we'll get to that hopefully a little bit in the end of this talk. You don't need Azure to use Kinect for Azure. Just let me clarify that at this point. It was launched at Mobile World Congress 2019, so we're already 2 years in the Azure Connect journey. Has better skeletal tracking, more joints and landmarks, and what joints are, we will see later on in this presentation. So this is roughly what the device looks like. I'm not sure if my camera is showing, but I'm holding the physical device into the camera also at the same time. But if you will be able to look at it maybe at the end of this talk if you still have time. Roughly, this is what the device is. It has a 7 microphone array. It has a casing, has an RGB camera, an indicator that there's actually camera streaming for privacy reasons, a depth camera, and infrared emitters. Yeah, so a bunch of screws and connectors, how that enable you to hook several of those devices in a chain configuration for signaling. Why that matters? If you have multiple Kinects in a room, they can synchronize the imaging taking and also the emission of infrared signals, so they don't do a lot of crosstalk. Like this is a blown up image of the infrared emitters and also the actual depth camera. This is the RGB camera, and this is a microphone array. That's the board here, right? So just a rough overview. Like an extra nerdy, there's some information out there that describes how actually a depth camera works. That's an article that you can read in the IEEE Micro. And in a nutshell, how it works is there is some light emitters, and the light emitters, well, they emit light with a specific phase, meaning it has a phase shift. And then there's a chip on the other end that receives the light back. So it sees basically from the reflections from all the real world objects, the light coming back. And so it can make a guess, okay, I get a light back here and it has this phase, right? And because that's so a specific phase signal, so it can make a guess on when it was sent out. And because it has multiple light emitters and not just one, it is able to disambiguate, is I think the term, the time the light took to pixel relatively precise in a specific range of distance. Again, read the article for all the details. It's really cool. And this is another more recent article and a little bit easier to understand, possibly at the Azure Dev Platform website, which is new, and I will get at the very end to the talk why you should need to watch this space. Okay, so basically that just describes the same thing. Here's the light source, sensor diffuser, the illumination model, the optical system, the imaging model, and then how it all plugged together, right? Roughly, what is the architecture of a Kinect application? Is you connect it to a device, which is typically right now a PC. We are here USB. For those who are extra nerdy, the sensor in the Azure Kinect is the same sensor that's also on HoloLens 2, but is optimized for different power consumption. So you will not have access to it like this in the same way in HoloLens 2, but and it doesn't have a USB connection there, obviously. So from the PC, the sensor SDK takes over to communicate with this device, and it doesn't install an extra driver. The sensor SDK actually communicates directly with the USB protocol. And on top of that, then there's various types of services you can use. You can use the body tracking SDK. You can connect it to some Azure services to analyze images, or you can just build up custom applications, or you can use Azure Speech Services with a microphone array. A little bit of a downer is that there's currently no good software available to make use of this microphone array, even though it's really powerful. It's the same as in the microphone that has been made public for Teams rooms. But yeah, so maybe somebody can come up with some cool software for it. Currently, there's nothing out there. So I will show more of this in a real life. So I will not go here, but roughly you have the microphone array output, the IMU, that's the acceleration emitter, and so on. That's the same thing you would find a phone that enables the device to know which direction it's pointing. Is it moving around? So you can mount your Kinect on a robot, for example, and be able to use that information to get additional information to move in an application. It gives you a color image, the so-called depth map. Don't worry about the rendering. So a depth map doesn't have color, just has distance information. But in here, they decided to map a specific distance to a specific color. And on then the upper left side, which is actually really cool, is the active infrared image. Active infrared means because the device, the Kinect, emits infrared, it's also able to know about the light it emits. And why does it know that? Because it has this phase shifting that I mentioned earlier. So it modulates light in a specific way, so it's able to re-recognize the light that it sent out. Meaning, if you have, let's say, like here would be an artificial light source in the background of the image, it would be removed. You would not see it. You would only see the infrared reflections from the actual Kinect, or maybe if you have some infrared reflective strips on your body that may confuse it a little bit, but in general, you see the infrared coming from the device. Infrared doesn't mean heat in this sense. It's a different wavelengths. The infrared spectrum is really, really large, and all that said, image recognizing only its own light, you cannot compete with the sun or with with a welding torch maybe. So there's some light sources that are a little bit brighter than the Kinect could compete with, even with all the tricks. The sensor SDK is also something that's relatively new for Microsoft. It's this low-level cross-platform, has been made available as open source. Mostly there's some small component that's not open source that deals with the actual dev data processing. And you can contribute on it or hack away at it on GitHub. It has interfaces available in C, which is the native language it's developed in C++ and in C#, and it's supported in Linux and Windows. Yeah, so that's actually pretty cool. It's also the best way, really, if you want to talk to the product team, go to GitHub and raise an issue there. That's probably the best way you get a response and you can interact with them. The sensor SDK tools, we will look at them. If you install the sensor SDK, then you get a Kinect for Azure viewer, which lets you view the raw Kinect data streams and helps you position your device and whatnot. And you can update the firmware, and it has a recording tool built in. So you could, in theory, record all the sensor data and play it back later and consume it in your own application, but we will not be able to show that in detail today. Again, ways to contribute. I would say today the best way is to use GitHub. This site was a little bit older, maybe. And let's have a look quickly at the at this Kinect for Azure viewer. So I'm starting it. And at the first thing you see, I mean, if it's a little bit small, I apologize. On the upper left side is you see the serial number of the device. It basically queries the USB you have, all the USB connections on your machine, and then you open the device. When you open the device, nobody else can take it. So that's a difference for Kinect for Windows version 2, where multiple devices, where one device could be shared between applications. We have a bunch of settings here. To summarize it briefly, let me just start some settings here first of all. So this means near field, basically field of view unbind. This is near field of view bind. The difference between combine neighboring pixels, so you get less resolution but also less noise. So this is unbind, so you see the flickering in the back. In theory, if I go to bind, I should see a little bit less flickering. Oh, Jiminy crickets, what did I do? Get an error message. Yeah, and flickers maybe a little bit less. Yeah, okay. And then you have also wide field of view. Let's start that. The difference is you see more of the room in the back, but you get a little bit of less resolution in space. And yeah, so that's basically what it is. It's optimized for different distances and different angles of looking at things. You define the resolution, the color space, and how many frames per second you want. You can also flip to a 3D motion, a 3D view of it. So this is basically my room here in 3D. Yeah, so but basically renders the coordinates of the depth camera into 3D space. But let's go back to this view quickly. What I mentioned earlier with the camera and being not impressed by light. So I turn on my cell phone as a flashlight here. You see the flashlight is on, but on the upper image there with the black and white, the infrared stream, you don't see the flashlight at all, right? You don't see the reflection on the table, so it's not impressed at all. Yeah, and you will see in a second why that matters. Let's go back to the presentation. Let me actually not forget to close the device. Oops, I hope I closed it. Close the application, but let's make sure I close it. Yep, it's closed because otherwise my later demos will fail. So for body tracking is an improvement over Kinect for Windows V2. You can track up to 15 skeletons. The limitation of that is not a physical limitation, but its limitation comes from how many people can you reasonably fit into the space that the Kinect sees. Yeah. Cross-platform developers is supported. Windows, Linux actually is not a preview anymore. You can just use it, and it has Onyx. It is basically Onyx runtime behind the scenes with support for NVIDIA or better hardware acceleration, but it supports also DirectML, Tensor RT, and CPU processing. Meanwhile, with different performance characteristics. I also ran it on an Intel GPU. Meanwhile, that works, but it's a little slow. So they meanwhile basically improved the compatibility to different graphics hardware. So let's talk about training briefly. So in the past, often when you were training depth cameras to understand human body motion or human bodies, often what people did, they had physical people doing specific motions in front of real camera. The Xbox Kinect was optimized for this scenario that you really stand in front of your TV and play a game or interact with the camera. So it was facing it. It wasn't optimized for you turning your back towards it or lying down or doing any motions that you wouldn't typically do. So what they did is now, because it's very difficult to scale to do labeling, it's very work intensive. Mostly they worked with so-called synthetics. So what you see here is, even though it almost looks like human people, are actually 3D models of human people that where artificially in the model markers have been put and animations were performed in code, and that allowed them to simulate different body types, different races, skin colors, people with maybe disabilities, and multiple environments very easily because you get perfect labeling with it. So that enables machine learning to be very accurate, to map the output, let's say, that this was generate to the expected body parts that you then wanted to train to recognize. Now, what do you train on? You train on something like this on the upper left side. So it's the sensor model. So that looks a little bit shady, and that's on purpose. So basically what they did, they transformed a rendering output into the expected color space or data space that the typical Kinect sensor would see. So with the cameras of the Kinect, this body tracking would work really well. With other types of cameras, it may not work as well. So that's basically a takeaway from it. So this is just a short comparison about the actual hardware and the systems, the methodology behind it. They use a different type of neural network now, and they support more joints. And the downside is the older Kinect for Windows V2 needed significantly less computing resources. The newer one requires a lot more power to run it effectively. So that's a little bit of a downer, but it's, well, but you get a lot out of it. That's really the takeaway. The question that I often get asked is like, oh, can you train it to recognize pets? Theoretically, I guess the team in Microsoft would be able to train it to recognize pets, but they would basically have models of dogs and cats and whatnot and do something like this and then train it for it. But it has not been done. If you have a business case and want to buy maybe a few million devices, talk to Microsoft. They may do it for you. Yeah. So looking back at the actual APIs, so this is what you get out of it. You get a collection of body structs out of the body tracking, and body index map, meaning the pixels that are associated with the recognized body, and you can do input capture. Yeah, 3D skeletons. This is roughly the processing, how it would work. It starts with a development kit, then you have the sensor SDK sitting on top of that, and that produces an active infrared image and a depth image. The convolutional neural network will, with the help of the Onyx runtime, do two things. The segmentation, meaning the pixels that belong to the body, and gives you two-dimensional joint positions. That's interesting, right? Why two-dimensional? Because they trained it for that, number one. And then they use the depth camera and the depth information from that to do something called model fitting, where they assign the third coordinates, the 3D coordinate to it, and also fix some things if a joint would be anatomically really weird. So that also means that maybe if you have a really unusual anatomy, maybe that's not, I don't know. I would expect that people with specific type of disabilities, where some joints may be a lot shorter or longer or amputated, may sometimes have funky output for some joints. So, but in general, it should work. Yeah, just something to consider. That's another view of the processing. So what you get the Kinect for Azure capture output. So basically the frame, you put it in a data queue. And then behind the scenes, the GPU will first do the convolutional neural network processing usually. Then the CPU will do model fitting on that output. And then you get a result in the results queue. And as a developer, you pop the result out of the results queue. That's just a view of the joints that you have available. Yeah. And this is a data structure for each joint that you get. You get a float. A float is just 3 coordinates for the position for each of the joints, and you get an orientation represented at a quaternion. I cannot explain too much what a quaternion is. It's basically 4 numbers that represent orientation in 3D space that is not affected by gimbal locking problems. And think of it similar to, if you ever remember complex numbers from schools, this is complex numbers on steroids, but it's very commonly used in 3D animation systems and 3D gaming engines and so on. Yeah. Scenarios for Kinect, a lot. I will not talk too much about them. You can you can find them out. So from kinematic analysis for rehabilitation, exercises, posture analysis, fall detection, all sorts of things where you want to understand motion of a person. Human understanding to get an idea what's happening in the space with people, tracking people, shopping behavior. Are they grabbing in the shelf and putting things back, for example? Or human computer interaction, let's say a video wall, or you have those nice, probably you've seen something like that before, where you wave to a video wall and then some birds fly or follow you or fly away from you. So you can do something like that from that. Or that's actually an interesting scenario, something like machine safety. You could use Kinect to make sure that the machine only runs if a human being is in a specific space far away enough from the machine. So walkthrough, I will show that quickly in code. In general, the process is, and that's a C code sample here. You give it some configuration, you start the camera, and that's it. But let's do that part of the demo in code. I have two basic demos for the Kinect processing. So what you do is you tell that's a C# API. So you can use the regular .NET code to develop against this. You tell it basically, hey, Kinect start camera with the device configuration. And this is pretty much what I showed you in that tool early in the talk, where you give it the color space, the resolution, if you want it binned or unbinned, if you want images from the different cameras to be synchronized and not. And then you get some information out of the Kinect. Oops, of course. I shouldn't have said step into, because of course I don't have this available as source code. And you get information back from it. You get the transform information, the color height, which is not surprising. That's the same we put, but in theory, the system supports that you query the camera, hey, what resolution do you have, for example. And then there's some plumbing. You set up the writable bitmap that you want to push data later in from, and you start the code. The start runs, and now we're waiting for capture results. So the capture result is basically the information as it comes back from the Kinect. And what we're doing here is we're just using that data as it comes back from the Kinect and writing it on screen through a more effective way, like through write pixel command, basically from memory block to memory block. Let's continue. I need to remove the breakpoint. Yeah, this is the output image. What I haven't shown you here, there's we are actually manipulating the camera output based on the depth information. So every I don't know 20 centimeters, we are cycling the color through. So that's the output of that example here. Let's go to a second example. I hope I didn't mess it up now. It starts the same way. You set up the system, and here we're masking the color in a specific way, and what we're doing here, that's where we actually use the depth information a little bit more meaningful. Basically, we're only rendering the data if it's in a specific distance. So a value corresponds to a distance in millimeter relative to the camera. So you would see now, basically, you don't see anything that's happening behind in the room, only what's happening between 0 centimeters and about 1 meter from the camera away. Okay. This is basically just done by simple operations on the pixels coming back from the Kinect. Body tracking walkthrough. It's similar to what I said earlier. Basically, you start the camera, then you create a body tracker. You hook it all together, and then you wait for the captures and push the captures into the body tracker, and then ask the body tracker, do you have a result? Pop the result from the result queue and process the result. Yeah. So again, what you also get is like a definition, is like an enum, or in .NET also an enumeration that helps you to access the different body joints, so you know which value, the first, the second, the third, coming back from the Kinect, because I mean it comes back as just memory locations, correspond to semantically to specific expected joints. And again, here's the data structure for the joints. So let's look at the body tracking demo quickly. Let's close the other one. This is basically a view application, and Something. Okay, what's happening? It just worked a second earlier. Okay. So you see it already is already set up. You see that the camera is running, but I don't hit a breakpoint yet because I'm not in the view, so there's no skeleton detected. So if I look briefly in Q, so basically this is the setup here. Again, we start the cameras at the beginning, it's the same thing, but then we also create a configuration for the tracker, which is tells it in this case, hey, I want the processing mode on the GPU, and I want my sensor orientation. You can also put it on upside down and so on. And then you initialize the tracker, and then as soon as we get data back from the device, we get the capture, then we queue that capture into the tracker, and then we wait until we get the result back from the tracker, right? And then we do something with that result. In this case, those things run in different threads, so we just initialize some data that we to be picked up in the background thread. So I'm walking into the camera view now, and we're hitting a breakpoint. So the other part of the program now has been, I mean, the queue got information back, got put in the queue, the result got returned. There's a bunch of code here that helps you to display things, but the core is that you get the frame from the Kinect, which has a timestamp. It's a little bit small, but I'm not going to mess around with zooming now because we really have a little time only. You get this body index map that I talked earlier about in a specific format. This is basically 8-bit format. And sorry, here it tells you the number of bodies in it. And then what you can do then, you tell it, get me the body on a specific index. You see not much here because this is just a memory buffer. You get the ID out of it. You can get the body colors, so assigned to that body as a vector. And then finally, you can iterate over the joins that exist for the body. We know how many joins to expect in total. And then we get the joins. Finally, we have something that we can look at in our .NET code, so which is again the position as a float and the quaternion as 4 numbers, right? And then we render the whole thing. I will remove the breakpoint now and walk into the camera. So here you see me, you see how it tracks my joints. I don't know how well the stream picks up live animation, but here, okay. Let's stop that and hope that nothing crashes. So example use cases, I mean, we talked about some of them earlier, but here's something that we implemented ourselves is, so when you build an application and want to understand the human body, you have a lot of components that you need to put together, right? I mean, if I walk through to it at the beginning, you have some side of sensor system and some type of high-level sensor processing and object classification, object recognition as one general topic. So that would map to, for example, posture classification by some templates or rules. You want to understand specific situations. You would implement situation recognition with some metadata. That could be, for example, activity levels, and then rules that you trigger depending on those activity levels, or you detect false based on a state machine. State machine could be like, hey, somebody is standing versus next moment somebody's not standing and only a short period of time passed. This would then be a fall, for example. And you hook all this up with a general understanding and model of the world. Okay, model of the world meaning you have physical formulas, you have metrics calculations to work with those physical formulas, and assigning numbers to specific observations that you get out of your system, meaning, for example, you need to make an educated guess about the mass of if you have a person in front of you, the mass, the weight of a person, to calculate forces at specific joints and so on. But it will make sense when we look at it in a short video later, and then eventually you render all this output, you put it all together, right? Body joint considerations, whenever you do something with analyzing joints, like not just rendering them, of course, you need to consider the tracking state. Roughly, that means the confidence, or if that joint has been relatively accurately measured, the system will also tell you if it has been more like guessed or referred. And then you convert it to something that you can more easily handle. For example, if you have a math framework that expects doubles, you then convert the data type. You want to understand the joint hierarchy, and then the real math gets important. Recommended literature is anything game development and game engines, because those have the best applicable fundamentals how to do something meaningful with 3D objects. Yeah, and game engines, for example, like Unity 3D, already do some things for you. Like you could simulate things hitting other things and do calculations based on that. And so, as I talked about assumptions, what we did in this case, we made assumptions that we found in literature, and based on NASA, when they designed the spacesuits, they actually created models and said, okay, a specific proportion of the body mass is typically in the arm, or from the ankle, foot. There are specific formulas to assign there, basically, in the proportions. And then we made assumptions that each of those body parts is roughly a rod, and that means, as a result, calculations on that, if you want to understand the human body, assume that rods or physical objects like rods interact, and then you need to make assumptions on what is the muscle efficiency when somebody moves. What does it really mean in terms of how much power they needed to, energy they needed to use at a body, at a specific joint. And that's really, really not trivial. So this is a very, very naive assumption, because we have tendons and ligaments and musculoskeletal system that's in some parts of the body really effective and other ones not. In some parts it really bounces back and conserves energy and plays it back, and others not. This is, if you want to understand more about quaternions, I recommend to look up YouTube videos. But basically, this is a type of math you would do on quaternions to represent orientations. Why it matters, besides of doing linear motion, velocity, acceleration, and so on, you could also do similar calculations also on angular motions, and then you would suddenly do math on angles or quaternions. Like you calculate acceleration in both, or force, which is torque. That if you have a car, you care about your torque. Then power or work energy, you can calculate all those things on also on angular motion. And it matters because you get different observations with different estimations of energy. And this will illustrate it roughly. This is a visualization of motion. You have little arrows here, and some arrows, the green arrows is velocity, the purple arrow is acceleration, if I remember right. And then at each of those joints here, those bubbles, those circles, as they move, is partially, some of them are circular motion, angular motion, and some of them are linear motion. Yeah. For example, you would see it as the arm here. Like right now, you have this, like right here, this green circle is angular motion more, and the other circles here is more linear motion, as it traverses more space. Why do we care? Well, the shoulder, for example, you saw was relatively stationary, but still, obviously, I needed force to move that arm, and we need a way to represent that. And you can get that by observing angular motions. Jitter is a big topic. I will not be able to show you a lot of it, but basically every type of sensor observation, you need to have some type of system to handle what do you do with all those erratic reads, because no sensor is really precise. If you just visualize a body, and it may look really, really good, but if you want to do math on it and calculate velocity between motion or acceleration, suddenly the smallest measuring inaccuracy or mistake will get you large differences. So you need to, in our case, we did a double exponential filter. And this will demonstrate a little bit why that matters. This is doing math like acceleration, velocity with filtered data. So here the check mark is on. And you see that we get relatively nice and smooth vectors, right? If we turn it off now, and I recorded that before, so that's not live. If I turn it off now, it's the same person, the same thing. You see all those arrows jumping around. This is just because of the inaccuracies that you get between different measurements. You can do too much with filters. Sometimes you may remove data that you care for, but overall, typically you need some type of filtering. And typically every system that has been released to do body tracking gets better over time, but consider that as something to do some filtering for better results. This is just a slide that tells you classification for activity levels and what that translates to in kilocalories and so on. This is a scenario for fall detection. Fall detection is actually really, really tricky because there are a lot of false positives and false negatives. Imagine you're falling down on the floor versus you're lying down because you're want to do sit-ups or you're tired. Or imagine you sit down on a couch or you jump on the couch really because you do that, let's jump on the couch and relax, and a system wouldn't easily be able to distinguish that. Yeah. So besides of really fancy AI, you can do some very, very straightforward calculations to between posture. Means your spine is straight and your legs are straight, more or less. They may be up to 45 degrees. Similar, if you're sitting, your spine is straight and your legs are probably some type, the upper legs 45, 90 degrees to the floor, maybe a little bit up, maybe a little bit down, but roughly in this angle. And lying down, you probably more or less your spine is parallel to the floor, maybe a little bit up, maybe a little bit down, depending on the angle, but doesn't go up. And you get a good idea about some basic postures without needing to train an AI with hundreds of thousands of measuring points. We actually measured energy expenditure estimation and that we tried to get from the code and compared it with some real life measurement. The real standard would be in like oximetry, where you measure the oxygen and the CO2 that has been consumed and burned. And we were able to see that, okay, different armbands, they measured different things compared to what our Kinect measured. Yeah, so there were quite some differences, and also depending on the motion type. I will get to that in a second. But after we analyzed the motion and the observations, we found a few things. We needed to both two things. We needed to do a different factor type on for the angular and linear motion to optimize it. And we got better matching to the observed results. But the other things we found is that, for example, for running in place, we overestimated the angular motion, and the linear motion was more aligned with the armbands. When for squatting, it was partially the other way around, or jumping and so on. So you may need to adjust your formula if you do something like energy estimation based on the exercise type you're observing. If you ever build a fitness app, think about that. So now finally, watch this space here, DevBlogs, Microsoft.com, Azure Dev Platform. There have not been a lot of new releases and update for Azure Kinect. So some people were like, oh my God, what's going on? Is it dying? But it's not dying. So what Microsoft is doing is you can buy Azure Kinect right now, but because of the global supply challenges, it's a so-called managed process. You need to tell Microsoft, I want to buy Azure Connect, and they will talk to you how much you want to buy. Yeah, but there have been announcements like with partners that will create Kinect devices, Kinect type devices. They're licensed the time of flight set, build devices for specific purposes. For example, here was a public announcement. And read about that a little bit. So there will be exciting things coming in the future. And but we're not there yet. I don't have in detail number either, but this is just a view of the partners here. The analog devices is, I believe, one of the more fundamental partners behind of it, and Orbeck is a well-known camera manufacturer that already exists. So you see a bunch of partnerships here, and this will reflect in futures of the Kinect platform. And the API will probably evolve also into supporting slightly different variations of the Kinect as it will come out in the future. So with that, if you have questions and answers, we don't have much time left, but a little bit we have left, so don't hesitate to ask me. This is my contact information, andreaserben@dnet.com. And the slide was from a different presentation, unfortunately, with the contact, but I hope you don't mind. I have more things to talk about, but now it's your space. Ask me.
Cool, thank you. So there has been one question during the talk, which was about can it track facial tracking or like expressions, and this came from Jos van Schaik, and I'll just put it here. And then actually Jasper Brackelsman answered it in the chat by saying no face tracking or gesture detection like the old Kinect version 2 SDK did.
We are all old friends, and I expected some friendly banter between. There's a very tight-knit community of previous Kinect MVPs that are now other MVPs or not MVPs anymore to do great work. Jasper Breckelman does awesome work around also motion capturing and so on. Look him up, and he has a great product around to make Kinect development easier. Basically, look him up, Jasper Breckelman. Breckel is
Breckel.com, I think it is.
Yep. So and Joost, of course, he's also one of the forerunners of Kinect and now HoloLens. Now, it's true that the previous Kinect had dedicated tooling for faces. Now, Microsoft, as Microsoft is, they change things, but they have stuff in Azure.
Wait, let me add the screen again if you want. Here we go.
So they have Face API available and computer vision available that gives you some face information, like you can do face recognition, face detection, including detecting landmarks in the face. I don't have this example is not very good. I cannot pull it up. Or maybe this is maybe better. Yeah, it gives you different landmarks in the face, if somebody's wearing makeup or not, or how blurry the image is, gives you an estimation about how old they may be, the gender, and a bunch of things that exceed what Kinect was able to do, but it's not free. Yeah, so that's the downside. You're using Azure for that. So I mean, your operating system has also a little bit of face stuff built in, but the old Kinect V2 was more powerful as in built-in face support here. That's true.
And in terms of feedback, I'll also put it here. Jasper says, "Great talk, by the way."
Thanks, Jasper. Like he will probably heckle me later on in private, but really.
I was already wondering because I remember both of them as well, and I was like, oh, should I send maybe a link to this session and then we can integrate them?
Yeah. So the other thing that maybe, I mean, if you read between the lines of Azure Devs platform, not Devs, but Devs platform, oh God, with my German accent and my Lisp together is also awful for those words, is that they're trying to make sense more of how to tie Azure together with Kinect and providing value for it. So and they probably want to also do something in Azure to support those different vendors that are now coming out with cameras. But again, you don't need to. Be happy to connect your a Kinect device to your Linux PC and start coding, and nobody will be upset at you. So no, I mean, they will still sell devices, and devices may not be the big business, but it still supports the ecosystem. So with that, I think I give time back to the audience to change rooms or for the next speaker to get ready.
Yes, there's actually the next speaker is already kind of here in watching your space. He's also from the Netherlands.
Okay.
Gerard, who says nice examples. And a last comment from Jasper. Great to see your app and how you use the linear and angular velocity for detection and measurements.
Mm-hmm.
And with that, stay here. And we're now going over to XR in the police. And thanks so much for your insights. And talk to you soon.
Ta-tu-ta-ta. Ta-tu-ta-ta. See you.